Hello and welcome. My name is Juliusz Straszyński, and this is joint work with Jakub Radoszewski about efficient computation of two covers of a string. So, identifying repetitive structure of a string is one of the key research areas of text algorithms, having applications in, for example, computational biology. It is quite clear that processing of a string that has a regular structure can be performed more efficiently, be it for pattern matching or data compression. The most elementary notion that grasps repetitiveness is periodicity. If a string can be generated by repeated concatenation of a smaller piece, then we say that it is periodic. Here, we have a period, namely a string ABA. Let us concatenate it several times. Now, the string is the fifth power of ABA. Finally, we say that a string is periodic if it has been trimmed from some power. That field of periodicity has been expanded upon by allowing not only concatenation, but also superposition. So, let's begin with a brief introduction to the required terms of quasi-periodicity. Let us begin with the notion of cover. So, we have some longer text, a little rectangle, and we say that a factor covers a text when all occurrences of the factor cover the string. Note that, as said before, occurrences might overlap, and this is important. In other words, each letter of the text belongs to some occurrence of the cover. And the notion of seed is quite similar. We say that a factor is a seed when it is a cover of some superstring of the text. Intuitively, we allow occurrences to go beyond the boundaries of the string. So, a linear time algorithm for computing the shortest cover of a text was presented by Apostolico et al. In Optimal Superprimitivity Testing in 1991. Later on, Moore and Smith showed that actually all the covers of a text can be computed in linear time in 1995. The notion of seed was introduced by Iliopoulos et al. In 1996, where they found representation of all seeds of a string in n log n time. But it was not until 2012 when linear algorithm was found by Kocimaka et al. Moreover, other variants of quasi-periodicity were researched as well, be it approximate covers, approximate seeds, covers in other models of computation, covers in two-dimensional text. Most recently, the scientific community focuses on these approximate variants, but in our paper, we have taken the other direction by considering an exact variant. This brings us to the main topic of the paper, two covers. Basically, we add an order of magnitude to the complexity of the problem. We want two factors of the same length to cover our string. In this case, we have red rectangles, ABAA, and blue rectangles, ABAB. Note that, as in the case of covers, occurrences might overlap. Basically, comparing to the original covers, some rectangles are just of a different color. And that is all. Precisely, we look for such a pair of factors of the same length, such that their occurrences cover the entire string. In this case, we see that the red rectangle is a prefix and blue is a suffix. Abbreviating prefix-suffix cover, we get PS cover. And this is one of the two cases. One of the strings always must be the prefix. But what do we do when the other is not a suffix? Something must cover the end of the string, so obviously the first string must occur as suffix as well. The second string must cover some space in the middle. Therefore, the blue rectangle is a border here. Abbreviating border cover, we call it B cover. In our paper, we show that we can find a two cover for each length, or all shortest covers in n log n log log n time, or all two covers in n log n log log n plus the size of output, and all in linear space. Now let us stop here for a bit. In the case of original covers, we have all n candidates, one for each length of border. One still needs to process them efficiently to achieve linear time, but it is quite imaginable. On the other hand, in the case of two covers, the number of candidates is n squared, and the answer actually might be of magnitude n squared. It's quite surprising that we can stay in almost linear realm with such expansion of the complexity of the problem. To give you some more background of the problem, in 2005, Cole et al. Have proved that the general case of lambda cover, that is, finding lambda-sized tuple of strings that cover the text, was shown to be NP-hard. To sum up, as said before, we have two cases of two covers. We'll begin with some key ideas of how to do the easier part, that is, find PS covers. So, unlike in the harder B covers, in PS covers we have only a linear amount of candidates, one pair for each length, a prefix and a suffix. Therefore, we'll try to iterate over lengths of the candidates and see what happens. At each length, some portion of the text is covered by occurrences of the prefix and the suffix. We'll take advantage of that fact that coverage of the string doesn't change too much when we increment the analyzed length. So let's say that we have some length L. Let's mark some occurrences of the prefix of length L. Now, what happens when we increase length by 1? It all depends whether the next letter at each occurrence matches the next letter in the prefix. Some occurrences persist. They get extended by one character, and some occurrences disappear. Here, occurrences with the next blue character persist, and occurrences with the next yellow character expire. What can we notice here? Basically, each expiration of an occurrence is an event, and in total, there is a linear number of those events. Let us proceed. Now, let's mark prefix occurrences as red arrows and suffix occurrences as blue arrows. This marks the direction in which they extend to. Moreover, it is helpful when we want to store them. If we identify the arrows with the tail point, when we increase the length, we don't need to do anything. We just need to remove expired occurrences. All other occurrences remain in place. Okay, so in our algorithm, apart from occurrences, we also maintain gaps. Given some point of the gap, we can easily calculate its boundaries, because we simply find the closest red or blue arrows to the left or to the right. Likewise, we can calculate the length when the gap closes. So it's pretty simple. Keep track of the gaps, and whenever an occurrence expires, just update gap expiration times. Return answer when there are no gaps. Well, almost. There's a problem. Some arrows are the closest ones for multiple gaps. In worst case, linear amount of gaps. Therefore, whenever we remove an occurrence, we have to update expiration times for multiple gaps. Obviously, we aren't able to afford that. Fortunately, we don't have to. Notice that for an arrow to close a distant gap, it needs to close gaps on the way first. Therefore, we can keep track only of the arrows in the closest vicinity, that is, in those immediate neighboring covered areas. Whenever a gap closes,
update information to the neighboring gaps. And that's all. We are able to keep locality to handle each event. So to reiterate, there are two kinds of events. First is an expiration of a gap. In that case, we must update neighboring gaps to propagate information about distant arrows. Secondly, there is expiration of an arrow. In that case, we must update neighboring gaps as well. Finally, using state-of-the-art data structures, we are able to perform each handling of an event in log n time, which brings us to the required complexity. Let's proceed to the harder case. So in the case of PS covers, one of the covering strings was a prefix, and the other was a suffix. The only case that remains is when one string is both a prefix and a suffix, namely a border. We can exploit this. In the case of PS covers, we iterated over all lengths, because we could afford that. Given length, we already knew what pair of candidates we needed to consider. However, here it's not that simple. If we fix some length, then of course we know what the border will look like, but the other string remains a mystery. There are just too many candidates. But as said before, one candidate is a border, and we can use this to our advantage. First, let us identify all lengths of borders and group them into exponential buckets. If we fixed exponent to be 2, for example, then we would get buckets 1 to 2, 2 to 4, 4 to 8, etc. Okay, but why would we do that? First, one might notice that a smaller border is actually a border of a bigger border. That's because it occurs here and there. And if length difference is too small, then the smaller border overlaps greatly with itself. Using Perdisi lemma, this implies that all the borders in the bucket are highly periodic. And we can use this to our advantage. On the other hand, if there is only one border in the bucket, then notice that we have only logarithmic amount of buckets. Therefore, we have still n log n time to spend to find the second string. Hooray! Let's focus on this case, leaving the periodic case for the most ardent of readers of our paper, as it is highly technical. So, we have some border of some fixed length, and we would like to find a string that would cover the rest of the string. So, let's pick some uncovered letter. The second string must be here somewhere, containing this very letter. So, if we pick two substrings here, of half of the required length, then the string we're looking for must actually contain one of them entirely. So let's choose one of them. Let's find all its occurrences. Finally, let's mark anchors at the beginning positions. Now, what do we have here? We have some set of positions. Each of them basically hints at where the second string might be. Each of them has some longest common suffix and longest common prefix with the original anchor. These arrows give some wiggle area for the second string. In the end, we do some kind of sweep algorithm to find strings which fill all the gaps between fixed covered areas. So I've omitted a lot of technicalities, but I hope that I gave you some hint of the key ideas of the paper. I wholeheartedly invite you to read our paper. I believe it's quite well written. There are some questions that remain. The first question would be, can you do better than log-log-n algorithm? A clean log-n would be the first step, and very nice result. We already have improved our result for the case of PS covers from log-log-n to linear time, but obviously B covers are still the bottleneck. Another question would be, can we do sub-square algorithms for free covers? What's the best we can do for lambda covers? What about lambda seeds? Maybe some interesting results can be done there. Is there some real-world data that is too coverable? And finally, the greatest question of all, can we do lambda covers in polynomial time? So that's all for me for today. Thank you for your attention. Bye-bye.